All right, hello everyone, and welcome to lecture number 10 on router internals and routing algorithms. Last time we talked about NAT, network address translation, and IP version 6, and these are basically, if you wanted to connect those two topics, are two different ways of dealing with the IP address shortcoming in IP version 4. IP version 4 only allows 32-bit addresses, so there are only 4 billion IP addresses using the traditional version 4 of IP. That's not enough for all the devices that want to use the internet, so network address translation takes a single public IP address and makes it available to many devices on a private network that share that public IP address through this behind this network address translator. We call that we distinguish between private networks and public networks because public networks or public IP addresses are on the internet that is reachable around the world. Private addresses only make sense within their network. If you try to use a private address outside of that network, you won't be, it doesn't make sense, and you won't be able to reach that machine using that private IP address unless you're on the same private network. NAT devices, these translators, use port mapping to make multiple machines on a private subnet look like multiple processes on one big machine. So basically you take that one public IP address and you assign different ports for the different connections on all the various machines. And a cool thing about this is that NAT doesn't require any awareness or cooperation from hosts on either side, so either your devices on the private side or the servers on the public side that are communicating. So it's kind of transparent in that way. NAT also can be used in a slightly different way, kind of in reverse, to implement a load balancer. And NATs are a class of devices called middle boxes, which are devices that handle packets without simply, aside from simply forwarding. So forwarding devices are routers, but if you do something different than forwarding, we call it a middle box. This includes firewalls and other security appliances in addition to NATs. And some NAT devices are also firewalls at the same time. Okay. Then we talked about IP version 6, which is sort of an upgrade to the protocol that uses 128-bit addresses, so addresses that are 4 times as long, which allows for an absurd number of public addresses, eliminating that shortage problem. But the big downside here is that because you're using much bigger addresses, the size of your headers in IP version 6 become much bigger, 20 bytes bigger. And that's one of the reasons why it's been, it has not fully replaced IP version 4. We saw in one experiment that about a third of internet traffic on average, if we take one measurement, is on the upgraded version 6 version of the protocol, whereas 2/3 is still on the old protocol. So they're not directly compatible, so in some sense they're two different internets using two different sets of addresses. And dual stack hosts use both IP version 4 and version 6 addresses to access, to use both of those networks. We can interoperate and send packets between version 6 islands using tunneling, and this is a way that this is one technique to allow version 6 of IP to become widespread without everyone adopting version 6, because you can use a version 4 path to transfer IP version 6 packets inside of an IP version 4 packet. Cool. All right, so we're moving on. So we're going to continue talking about routing, getting packets from end to end on the network, except now we're going to look more at how individual routers work. And in the second half of the lecture, we're going to start talking about how we determine rules. But just to review what we've learned so far about routing, we have the IP protocol that assigns an IP address for the source and destination of the packet. And that destination IP address is what we're going to look at to try to figure out what path that packet should take. Routers do that work. So a router has a forwarding table that was determined somehow by a routing algorithm. Again, we'll talk about these soon. But we have these address ranges that were determined to be associated with different output links, so that different addresses are sent in different directions. That's the forwarding table. Lets the router decide where a packet should go and what direction a packet should go, because in general it has multiple choices of where to send packets. And by setting the forwarding tables correctly in all the routers all around the world, we can have an internet that works and it's interconnected and efficiently gets packets to their destinations. Right. Okay, so let's talk a little bit more about these routers. So we're going to be talking a little bit about ports on routers. And this word ports is kind of overloaded in the sense that it means two different things in networking. In this lecture, we're going to be talking about physical ports. So think about a device that has many wires plugged into it. So this device has 4 different Ethernet cables plugged in. And we call each of those sockets or connections ports physically. Previously, though, when we're discussing TCP and UDP, we used the term port to distinguish between different connections on the same machine. So those were logical connections and logical ports that had numbers. And I say logical because they're not physical things. They're just abstractions of the traffic on the network. And but yeah, today we're going to be talking about ports in a physical sense. So when we look at these physical cables, again, we can translate from a picture to a schematic. This is a schematic view of a router with 4 connections, 4 links. But most of these links are actually bidirectional. So even though we draw it with one line, what we really mean is that there's a channel going in and a channel going out at each one of these ports, which I've drawn as tubes, okay, in the great tradition of the internet. So we can simultaneously receive traffic and send traffic, receive zeros and ones and send bits on the same cable. So they're really 2 cables in one for the 2 directions, okay? And we kind of rearrange those arrows. The same 4 links in both directions can be split in this final abstract view, putting all the input ports on one side and the output ports on the other side. So we take each cable and its input port is on the left side of this abstract view and its output port direction is on the right hand side. And the router itself is in the middle. So on all 4 of these cables, data can come in. Those are all shown on the left here as input ports. And data can also flow out on all these same cables using the other channel, the other direction of this medium, and those are the output ports we see on the right-hand side. And we've spoken abstractly about routers having a queue of packets that were received and are waiting to go out. Now, of course, we also need to decide which of the output ports to send the traffic on, right? And that's the routing decision we're making. Cool. So we started off with a simple router model with one queue, but today we're going to be breaking that down and looking in more detail about what's really happening. I mean, not in complete detail, but just a little bit more detail to give you a greater sense of how packet loss is not uniform across all the ports. So for each of these 4 ports I'm showing here, we actually are going to have typically a separate queue. Okay, so for each input port has its own queue, and those input ports have to be connected to output ports. Those output ports also have their own queues, and there's some kind of interconnect, some way of connecting the input ports to the appropriate output ports, depending on what the forwarding rule tells us, so that we can send data that came in from one port, out to any one of the other ports. Okay, and we'll talk a little bit about what this interconnect is in a second. Okay, and we'll also talk about the details of these ports. Before we do that, though, let's think about the first generation of routers, or a simple router that you can even build yourself out of any computer that you have, as long as you have a computer that has, let's say, multiple NICs or network interface cards, multiple Ethernet ports or wires that you can plug into it. You can implement a simple router on a computer using software. So as long as you have some software that accepts the packets, decodes them, looks at the IP addresses, and can implement some forwarding rules. For example, Linux's kernel has a built-in routing capability that's controlled with the IP tables command. So you can take any Linux server and make it a router by using the IP tables command to configure what range of IP addresses should be sent to which interfaces. And this is assuming that you have many. This would, it only makes sense to really do this if you have multiple network ports on that machine. Okay, but this design using a traditional computer is not really very efficient. we think of computers as being fast, but we want to do much better than what a single CPU can do in terms of processing. Okay, in this design, the memory of the machine is going to be a bottleneck and the memory bus is going to be a bottleneck, and the I/O bus for transferring data between the ports and the memory where the CPU can operate on them. Okay, so a router that can achieve higher performance doesn't rely on a single CPU to examine every packet. It does things in parallel, and it uses this design with input ports being connected to output ports with a high-speed switching fabric. There also is some kind of processor that implements the control plane, which is to say decides the routing algorithms. We're going to be talking a little bit more about that later in this lecture and then in following lectures. But let's not worry too much about that yet. For the most part, we have ports, input ports and output ports. Those ports each have a copy of forwarding tables, which are the rules to decide where packets go. That's in this, and those are determined by the routing processor and shared to all of the input ports that decide that actually implement the forwarding rules. So the data plane of the network, which is to say the implementation of the forwarding rules, happens in parallel on all these input ports that have their own processors, and they have a copy of the rules that were determined by the routing processor. And determining those rules is called the control plane. That's done by algorithms like BGP, which we'll spend more time talking about in later lectures. Okay. To zoom in on one of those input ports, it was shown in the previous diagram with 3 boxes. Basically, that's not too important, but you have a physical wire coming in, and there's some circuitry needed to convert from that signal that comes in to zeros and ones into packets. And how that works will depend on the physical implementation, like if you're using a radio versus Ethernet on Cat5 versus a fiber optic connection, whatever, different circuitry there. And then there's a link layer protocol, which we'll talk about later in the class, that gets packets out of the zeros and ones. And then, once we have those packets, today we're focusing on the data plane of IP, where we take those packets, do a lookup, check a forwarding table to see what output port they should go to when they get to the head of the queue. So we have a queue to store packets that are waiting to be processed, but at the head of the queue we can process each one of those packets, look at the destination IP address, and make a choice about what output port should be used. Now, we have to then get the data to that output port. And the switch fabric that connects all the inputs to all the outputs is going to be where we send that packet. Okay. Now, keep in mind, this input port, you can think of it as its own little independent computer working in parallel, and all the input ports can do that. So inside this lookup and forwarding and queuing module here, we have memory for queuing, we have a processor for examining the packets, and we have memory also for storing forwarding tables, and we implement those forwarding rules here and we annotate each packet with its destination output port and put it on the switch fabric to be sent to the right output port. We want to process all of these ports at line speed, meaning as fast as they come in, so the queue doesn't fill up, right? And the more input ports we have, the more we can do in parallel. But we'll see the switch fabric can become a bottleneck. So the switching fabric is the connection between all your inputs and all your outputs. And this is a very important feature of a router or switch. So switch and router are two kind of interchangeable terms. What we're talking about today are really routers, which are sometimes called layer 3 switches. Layer 3 refers to IP in the traditional layering numbers that are assigned to different protocol layers in networking, which we're not using too much in this class because I think it's kind of out of date. Anyway, so this switching fabric has a switching rate, which is the maximum. The switch itself, the whole device, whether you call it a router or a switch, has some peak amount of data it can handle from all of its inputs to all of its outputs at once. We call that the switching rate. So ideally, it would be you would allow all the inputs to work at their full line rate. Like there's some maximum bit rate there's some bit rate of all these input lines, and for all of them to operate at the same time would be ideal to be able to handle that. You're not necessarily going to achieve that. You might design a system that allows the line rate that handles higher line rates on the individual lines as you can compare to more than what you can handle on average from all of them at once, because you don't expect all of them to be busy at once. In order to support all of them at once, you need an interconnection in between that is really fast, and that could be expensive to build. Okay, there are two, and we'll see two basic designs to try to give you an intuition for why it might be difficult to build a fast interconnect or switching fabric between the inputs and outputs. The simplest design is a bus, which is to say we just kind of have a set of wires or a wire that all the inputs and outputs are connected to. So if you want to send data from an input to an output, you have to use the bus, and only one input port can use the bus at once. So for this to work well without really slowing things down, your bus should be faster than your input line speeds. So this bus could be, let's say, 10 times faster than the line rate on the inputs, and that would allow you to handle 10 input ports operating simultaneously at full speed. It could be slightly slower than that total input line rates, but then that would limit your switching rate there. Okay. An alternative to a bus is a crossbar. In a crossbar, what you have is the ability for data to flow in parallel between multiple input and output pairs. And we'll see more about that, how that might be implemented in a second. Okay, yeah. So with a crossbar switch, instead of just having one wire that's shared, one bus that's shared between all the inputs and outputs where they have to take turns using it, you have wires laid out from each input that can be connected to every output. So you have basically an n by n grid of connections where at the intersections you have a switch that can be opened or closed. So you have the potential to connect any input to output. With the open circles, I'm showing open connections, and the closed circles are closed connections. So here I'm showing input 1 with data flow with a connection to output 2, this blue wire. And to make that connection, we close this point in the grid here to allow this electrical connection to connect to this electrical connection, but not to connect to the other ones. So simultaneously, we can connect the second input port to the third output port by setting this switch here that I'm showing to the on position, but leaving the other ones off in both the X and the Y direction. And finally, that also allows, there's nothing to say that we can't also have data flowing between these other two unused ports, which we haven't used so far, input 3 and output 1, right? So this is better in a sense than a bus, because we can use all the outputs at the same time. We can send data to all the outputs at the same time, and we can pull data from all the inputs at the same time in parallel. This is a lot more parallel than the bus design, but there's a lot more complexity to this crossbar circuit than there is in the regular bus. Okay, so we have n squared switching points here. You can imagine that as we scale this up to more and more input and output ports, the ability to pairwise interconnect all of them in parallel gets more expensive, because the complexity of the circuit goes up like n squared. So notice in the bus design, did I mention this? Yeah, in the bus design, you can see in the bus design in particular why you need a queue in the inputs, because you need to, if this bus is faster than the input line rate, you want to be able to store up a full packet of data and then send it quickly on the bus to an output port, and then move on to sending another input out. Yeah. So you can kind of think of a road analogy for switching fabrics, these two switching fabrics. A bus is like a roundabout. I don't know if you've seen those on American roadways. They're not very popular, but in other parts of the world, they are popular. This is where you have many different roads that are connected by a common, basically one road or a circular road here. This is the bus. The roundabout is the bus. If you want to go from any input to any output, you have to travel through this shared resource, and the shared resource has limited capacity. Okay. A crossbar is like this is called a stack exchange, which is like the most complex kind of roadway interchange, where every possible pair of input and output has its own dedicated connection available that can operate in parallel. But obviously it's much more expensive to build the stack exchange with all the bridges and stuff compared to the roundabout. But if you could somehow make the speed limit in the roundabout really fast compared to the speed limit on the side roads, the roundabout would actually work just fine in terms of handling the maximum amount of input traffic you might see. Okay, so on the output ports, we also have buffering, which is to say we have queuing. So a packet is pulled off the switch fabric and to be sent out onto the line. And we still have, of course, a translation from packets to bits and into electrical signals. But this output line has a certain fixed bit rate usually, and a link layer protocol also may have some rules for waiting to send if the output line is busy, like for example for using radio. We'll talk more about link layer later. But for both of those reasons, packets might need to wait before they're sent. So there's queuing here. If the output line is not quite, has limited speed and more data is coming in than can be sent, it will get queued up here in this queue. Okay. Now, with any queue, actually, whether it's input queue or output queue, but especially in the output queue, you can have a policy that distinguishes between the different packets and sets priorities. So instead of just delivering them first in, first out, you can schedule the packets and say, okay, if it's a certain type of packet, I'm going to pull it off the queue more quickly than if it were a different type of packet, and therefore give higher priority. By doing that, there's also less chance that type of packet will be dropped. Okay, that's called packet scheduling, and giving different priorities to different types of packets. When I say types, it could be what port is being used, which is to say what protocol. Could be certain IP address, source or destination could get higher or lower priority. All those kinds of rules are prioritization of your limited output capacity. Differentiation of service. So net neutrality, you've probably heard of, is the policy debate in government, especially in the US, about whether internet service providers are allowed to differentiate between different classes of traffic and give higher priority to different types of traffic. And in the US currently, net neutrality is not a law, so net neutrality is not enforced. So ISPs can do whatever they want currently in terms of providing inferior service to certain customers. And so maybe if you think of a place where this is important, the dominant home internet service providers are often cable companies, which are also in the business of delivering traditionally television services, right? So like I get my home internet connection from Comcast, which is a cable TV company. So Comcast, in order to support their television business, might think it was a good idea to provide really slow service to Netflix traffic, right? Netflix is their biggest competitor sort of in television in some sense, or is one of their big competitors. So without net neutrality laws, Comcast is allowed to provide their customers with really poor Netflix service if they want to do that. I'm not saying they do that. I haven't seen, but that's a possibility. And the way they would do that is in these output ports by having rules that drop the packets from Netflix more readily. I mean, they could even do it maliciously, but in general, they could just do it when there are multiple packets to choose from that could be sent. They might just decide never to send the Netflix packets if there are some in there. Okay, so we've said from the beginning that routers have queues, and when queues are full, packets get dropped. But we can, now that we have a model of input and output ports and switching fabric, we can get a little bit more detail. Think about in a little more detail when exactly packets are lost and which packets would be dropped. So there really are two different network resources that can be overloaded here. One is the switching fabric. Okay, this thing in the middle that connects the input ports and the output ports. If you have a lot of traffic coming in across all the ports, and the line rates of the summing up those ports is greater than the switching fabric's rate, which in general will be true, then these input port queues could fill up and drop packets. That just means, and the problem there is just that there's too much data coming in aggregate across all the input ports. So the input queues would fill and drop packets. Another source of packet loss that's more targeted could be at specific output lines. So this upper rightmost output line, there could be a lot of traffic that wants to flow out here, that's coming from all the different input ports. A lot of traffic is being sent through the high-speed switching fabric to this particular output port. But this one line is not at this moment, fast enough to handle all the traffic that at this moment is coming in. So the queue fills up here, and this queue drops traffic. Okay, so in both these cases, packets will be dropped silently. We mentioned in some homework discussion that maybe explicit congestion notification bit could be set to notify the sender that the queues are getting full. These are the queues that we're talking about. It could be any one of these queues, actually, for explicit congestion notification. All right, so to review, if this line on the bottom right is too slow, if we slow this down a lot, what'll happen to the packets flowing throughout this router? So stop and think about that. So there are two different types of packets. Basically, the ones that are flowing to this output port will get queued up here beforehand, and this queue will get full, and packets will drop off of this queue. Now, other traffic that's going to other ports, like this top right port, that traffic would not be affected. So for traffic that's flowing out in a different direction, there would be no packet loss, while on the other traffic flowing in this crowded direction could be experiencing packet loss. So just because there's packet loss on this router at this moment doesn't mean it affects all traffic, but it could just be affecting traffic that's flowing in one particular direction, right? Because it's one of the many queues in there that's overloaded. Not every queue is overloaded, just one of the queues is overloaded, and that pertains to just a particular direction of traffic. Okay. So I talked about, when I was talking about net neutrality and prioritization of traffic, one way to implement that, differentiation of traffic is with weighted fair queuing. It's a pretty simple idea. What we do is instead of having one queue, we break the queue into many queues, different classes of traffic. So when packets come in, instead of just sticking them in the back of a queue, we classify them first. So this diagram shows packets coming in, being classified, and when they're classified, we have a rule that decides what class they're in, high priority, second priority, third priority, whatever, or they just have different names, and they go in separate queues. Now, the purpose of doing that is to give higher priority to some of these classes. We don't just split them up for no reason. And the way you can implement that is with weights. So if each queue has a certain weight, this picture diagram shows them W1, W2, W3, and you have a scheduler that kind of goes through and spends W1 time on the first one, W2 time on the second one, W3 time on the third one. So in other words, the amount of time that's spent sending packets off of each queue is proportional to its weight, and you kind of go around in order. So if this first one has a high weight, we spend a lot of time taking packets off this first queue. Eventually that time expires, the time corresponding to the weight. We move to the next one, spend a little time there. Maybe it's less weight, so there's less time there. We move on to the next one, spend a certain amount of time, whatever specified by this weight there, and move on. If we keep doing that, then it gives higher priority to those queues with higher weight, to those classes of packets that end up in that class. It's simple to implement. You can use different rules like IP addresses, port numbers, whether it's TCP versus UDP. For example, UDP traffic, you might want to give low priority because UDP traffic it doesn't have congestion control, so it can easily overwhelm the network. Or you could have an explicit quality of service flag that's being set by routers on the IP header. We haven't really talked about that. That's not super important. So you'll spend a constant amount of time proportional to the weight on each class of traffic. And by doing that, actually, you can prove there's bounded wait time for all of these queues, although the expected wait time is longer if there's less weight on each queue. All right, so that was kind of a little bit of a view of what goes on inside routers at the in the data plane, at the data layer, in terms of how forwarding is implemented and queues and connecting inputs and outputs. Not a ton of detail, but just a little bit more. So we're going to move on to a new topic, so a new chapter on the IP control plane. In other words, how are forwarding rules determined? If you want to take a quick break, this would be a good time to do that because this is a new topic. All right. So we're going to be talking about shortest path algorithms, basically, because with the internet, what we're trying to figure out is we want to get packets from a source to a destination as quickly as possible across the network. Okay, we're going to have centralized and distributed ways of doing that, centralized and distributed algorithms for computing shortest path, and with centralized routing or algorithms in general, we have algorithms that have the full knowledge of the entire network. Like if a machine knew what the whole internet was at that moment, what all the connections were, what the distances were, and everything, it can make a decision about what path to take. That would be a centralized or global approach. We say it's global because it makes a decision with knowledge of the whole world, right? And those decisions made in that one place with all the information could be propagated to all of the routers, so that because you have all the information, you can make it the best decision for everyone and tell everyone what that best decision is, right? The outcome. In routing, we call these link state algorithms because they are aware of all the full link state in the network, which is to say that they know everything going on in the network. And these are used within an organization, internal to an organization, which was called an autonomous system. We'll come back to that term later on. But within an organization, within the routers that are controlled by a single organization, you can use algorithms that take advantage of all that information. But across the whole internet, we don't ever really share all that information in one place. It's just too much information and it changes too quickly to ever get that in one place. And it's hard to trust that information too. So instead we use distributed algorithms for routing, which you could also think of as local routing algorithms. Like you have information about your locality, just your neighborhood, and you use that to make a decision about where to forward traffic or what the shortest paths are, kind of. Except you don't really have all the information about end-to-end. You just have the next hop observations. And these operate iteratively, so you have a little information, you share it, you get a little information from your neighbors. As you get more information, new information, you update your information and continue. So BGP does this. That's the main algorithm used for routing across the internet at the global scale, which we have a couple lectures talking about. So distributed algorithms are more difficult to design correctly because you don't have all the information you need, but in some sense they're better suited to this global routing problem because they allow things to happen in parallel without like cooperation of everyone, without sharing a ton of information. So that's a brief overview, but today actually I'm going to be doing a little bit of like a graph theory lesson almost, I guess a mini algorithms lesson on shortest path in networks. So there's going to be a portion of this that's like classical, traditional algorithms for shortest path. And if you've seen that already, bear with me, and you can go through that quickly. There's one part at the end that's going to be new for everyone, regardless of whether you've taken an algorithms class or if you're an expert in graph theory or graph algorithms, whatever. Okay. But so let's start off just with some basics to get everyone on the same page. We're going to be using a graph abstraction of computer networks, and hopefully you've seen this in either discrete math or data structures or something. So we have vertexes and edges. So the graph G is the tuple of the vertex set and the edge set. And in this case, the vertexes represent routers. So the points in the graph are the routers, and the links are the edges are the links that connect the routers. And they have weights, those numbers that you see. The weights represent the distance between routers, which we'll think about them as the cost to communicate, but for the purpose of this exercise, think of it as time. We're trying to minimize like the time it takes to get a message from point A to point B, or in this case, point X to point Y. We're actually not going to worry about capacity, because links do have limited capacity, but that is mainly controlled with, we're going to assume that TCP congestion control prevents overload of a network, but within that bound, the routing choices are going to be made that minimize the latency without any respect to maximizing throughput, actually, which is pretty interesting. And in the big picture is like suboptimal, because maybe what you want to do is optimize throughput. In practice, there are a lot of ad hoc decisions made by networking companies about where to place links and how to set routes to deal with maximizing throughput. But these algorithms, the automated operation of choosing paths is based on minimizing the delay from point to point, which is to say the sum of the edges. Okay. So, yeah, I'm going to use the letter C to represent the cost of an edge. C means cost. What you can also think of as distance. So the shortest path problem on a graph is, given a edge-weighted graph, in this case we're using an undirected graph, we have a starting vertex and a destination vertex. So let's say X to Y. We want to figure out we want to find a path from X to Y, which is a series of edges that together connect the two. I mean, informally speaking. Where the sum of weights of those edges is minimal. Okay, so in this particular example, the minimal path, the shortest path, goes through B and D through this bottom, because we have 1 + 1 + 2 gives us a path of cost 4. And if you kind of look around at all the other options, there's no way to get from X to Y in less than 4. Okay, this is you could try to, with 3 you could get up to C, but once you get there's no way to get from C to Y in less than 4. You have to go back actually this way. So 4 is the best. And we do need clever algorithms, because we can't do simple things. Like if we used a greedy approach, in this sense, by greedy I mean you just like follow the shortest edge that gets you toward the end point. If you used a greedy approach, that might take you from D up to C, because there's a cost of 1 to get there. But then from there, that takes you out of the way. That's not the best way to get to Y. Okay, so we need somehow to find correct and efficient algorithms to do this. And I want to mention 2 algorithms here, plus a third one, which is a distributed implementation of it in this lecture. And they're all based on one simple insight for the shortest path problem, which is called the Bellman-Ford equation. But basically, the point is that we can break the shortest path from X to Y into we can express the optimal solution in terms of subproblems, which is to say shortest paths from the same source to different destinations. So if I want to find the shortest path from X to Y, it's going to turn out to be helpful if we know the shortest paths from X to other nodes in the network. Okay. So in this particular case, if I want to find the shortest path from X to Y, so the expression for that I have is dxy. This is the shortest path, the distance between X and Y, meaning the minimum distance. The answer for that, the solution to that, is going to be the minimum is going to be either one of 2 options. Either I have to, if I'm going to get from X to Y, either I'm going to go through C or I'm going to go through D, right? Because those are the only neighbors of Y. So I'm either going to go from X to C plus CY, or I'm going to go X to D somehow, and then D to Y. Now, how do I get what's the cost? And then I choose whichever one of those is minimal. Basically, is it cheaper to go through C or cheaper to go through D? And I can compute that again in terms of the subproblem. So the cost to get from the shortest cost to get from X to C is dxc. So if I somehow have already figured out the shortest path to get to C, I can use that number plus the edge 5 to get that alternative. So okay, if I'm going to go directly from C, it's going to be the cost to C plus 5, or I can go to D, so it's the cost to get to D plus this edge 2. Okay, so I'm adding one edge, which is the final hop, plus the shortest path to get to the neighbor. Okay, so I can choose between these. Yeah. And I'm just going to choose the minimal. Okay. So this sum I have here is the sum of the path that almost gets there plus the cost of the final step. And I'm going to consider every possible way of almost getting there, which is to say every neighbor, the cost of that final step from the neighbor to the destination plus the cost of what it took to get to that neighbor. Okay, and that'll give me a recursive form of the problem, which I can then solve in a couple different ways efficiently. Okay, in general, so that last example just expressed it in terms of C and D, two different neighbors. But we can apply this across an arbitrary network with, if we just change this equation to say the distance between two nodes is 0 if those two nodes are the same. So this is just the base case where you're going nowhere, right? The cost to go nowhere is 0. Otherwise, it's the cost to get to some neighbor V. So we're minimizing across every possible V, which is a neighbor of the destination Y. Or actually, in this expression, it doesn't have to be a neighbor. Just across every other possible vertex, what's the distance to get from the source to that other vertex plus the cost of going directly from that other vertex V, that candidate we're considering, to the final destination. Okay. So just to express that in a different way, or again, it's the shortest path between X and Y must pass through some vertex V that's adjacent to Y before finally arriving at Y, and we just choose the one that's minimal. Okay. So the algorithms we're going to look at basically are going to consider every possible V and implement this recursive solution using dynamic programming by basically building out these. We can't, to make use of this recursive formula, we have to start off with the base case and build up some distances that are short that we know to be correct, and gradually make them longer by adding additional steps. Okay. So the first way of doing that is called the Bellman-Ford algorithm, and it's one of two different dynamic programming solutions to this shortest path problem I'm going to show you. So there's a array distance that we're going to keep track of, that we're going to build out throughout the operation of this algorithm. So distance sub I is the distance from the source to another node in the graph. We initialize it to 0 for the source to itself, and for all the other vertices, we initialize it to infinity. So at first we don't know of a way to get anywhere except for to the source. We have this previous pointer just to track the predecessors in the shortest path. But what we do is we loop through. We have n-1 iterations of this algorithm, or stages. And in this outer loop, at every iteration, we're trying to build out the length of the paths where we have the optimal shortest paths. So basically what we're saying is we start off with paths of length 0, and we know after this initialization, we know the shortest path to get from the source to every destination, assuming that the paths we can use are no longer than length 0. Okay, so that gives us either 0 or infinity. In this loop down here, the main loop of the algorithm, we're lengthening the possible number of steps we can use in the path. So we say, okay, let's consider making our paths a little bit longer. When we do that, we go through every edge in the network, and see whether that allows us to do what's called a relaxation. A relaxation is when we try to use an edge to get from the source to the destination and create a shortest path, to create a path to that destination that's shorter than our previous best known path to that destination. Okay, so we have a previous distance from the source plus the cost of the edge we're considering. That gives us a candidate distance to the destination. If that's shorter than what we previously knew was the shortest path to the destination, then we set that as the shortest path. And we keep doing this. If we do this n-1 times, eventually we will get the shortest paths of maximum length up to length n-1, which is going to be, if the shortest path in a network of length with n nodes is never going to be more than n-1 edges. So the invariant here is that at round I, considering this for loop here, at round I, this distance array that we're building has the shortest path from the source to destination j that has at most I hops. Okay. And the runtime complexity here is easy to see just by summing up these two loops, is the number of vertices times the number of edges in the worst case. Okay, so to see this work, let's look at a simple network. Okay, draw this out. So let's say we have this like a diamond-shaped network. Okay, like so. And we have, this is the source, and this is the destination we want to get to, the final destination. Let's put this in focus. Okay, and we have some costs on these edges. So let's say the cost here is 1. The pen is no good. Let's try a different one. The cost here is 1. The cost here is 2. And this is 3. I'll just make these blue so they're all the same. The cost here is 1, and the cost here is 1. Okay, so we know that the solution we want to get is going to be, this is the shortest path here. Okay, this kind of zigzag thing. The shortest path is 3. That's 1. Actually, this one here is equivalent. So either one of these is equivalent. Actually, just to make this, just to break this tie, I'm going to make this one 3. Okay. So, like I said before, the way the algorithm works is it goes through n-1 loops, where each time we have paths, optimal paths of length I. Okay. So initially, I'm going to use this green color to say how we initialize the distance vector, and I'm gonna mark it on the edges. So the distance from S to S is 0 initially, and all these others, it is infinity. Okay. So I know that with the path of length 0, I can get to this node in cost 0. To these other nodes, I can get to them in cost infinity, because I can't get to these other nodes in using so this is time equals 0 or iteration 0. So path of length less than or equal to 0. So these are in fact the correct distances used with this limitation that the path has to be lesser than or equal to 0. Okay, now I start the loop. So I guess this is I go to I equals 0. So again, I'm going through this loop here. That was the initialization. Now I'm going to go through the main algorithm. I'm going to make I go from 1 to n-1, and we're going to see that we're increasing the length of the paths that are possible, that are allowed. Okay, initially I only allowed paths of length 0. Let's try paths of length 1. So the way we do this is, it's the same every time. We just go through, we consider every edge in random order. It doesn't matter what order we go through the edges. But for each edge, we do a relaxation. What that means is, let's say we start with this one here. We say, okay, let me take the source and and add to it the cost here and see if that gives me an improvement for reaching the other side of this edge. And I guess since these are undirected, I have to do them in both directions. So I say infinity plus 3 is infinity. Okay, infinity is not less than infinity, so it doesn't matter. Infinity plus 3 is infinity. That's not less than that one, so it doesn't matter. So this first edge that I just considered, I just tried this relaxation in the middle, and I did it in both directions. I guess, so I'm going through each edge, I would do UV and VU. That gave me no improvement, so I made no change. And actually, in general, if we do that to any edge that's connected to two infinities, it's going to give us the same thing. But nonetheless, the algorithm will go through all of these. We don't know what order, but let's just say it goes to this one next, this edge in the upper left with cost 1. Now, the relaxation it can try here is it can say, if I take the one end of this edge, 0, add 1 to it, I get 1. So now, in other words, using this edge, I know that I can reach this point here in cost 1. Is that cost better than what I previously thought I could reach this node? Yes, it is, because previously I thought it would take infinity to get here. But I just found a path that's cost 1, 0 plus 1. So we're going to change this to 1. Okay. And we could try the reverse direction, but in that case it doesn't help because we get 2, which is less than, which is more than the 0 we had here. This edge here, why don't you stop and think, what'll happen when we do the relaxation of this edge? Okay, so we'll get 0 plus 3 is 3. 3 is less than infinity. Remember, that's that test here, 3 less than infinity. Infinity is what we previously had as a distance. So that means we will change this to 3. Okay, so that was at the end of stage 1. So at the invariant now, we finished iteration 1. We now have marked on these nodes in green the shortest distance we can reach all these nodes from the source using paths at most length 1. And if you look at this, I mean, that's true. This is operating correctly. And we just keep doing that. You know, when we get to 2, we'll find that we can get, for example, we can get here 3. We'll find we can get here in cost 2, right? Because we'll have a relaxation of this edge. We'll say 1 plus 1 is 2, which is less than this 3. We'll do a relaxation here and get, we'll change these infinities, you know. This infinity will change to, depending on the order we do it in. If we do it in the wrong order, we could actually get ahead of ourselves and find the shortest path here. But let's say we checked this one first. We would see, you know, if we did this edge before that edge, then we would get 4 for this. But if we did this edge first and then that one, then maybe we would actually get 3, which is the final solution. Okay. So that's in a nutshell how the Bellman-Ford algorithm works, and you have to run it until I equals n minus 1 to make sure that you are testing paths that might be up to the highest possible length. Okay. And at home, I suggest you check out this web page for some demonstration of Bellman-Ford in action. You can click through and see it work on some sample graphs, which is pretty cool. Okay, so the other variation of shortest path, which actually in some sense is better because it's more efficient, is Dijkstra's algorithm. This is a classic example of dynamic programming. And okay, but it's a little bit harder to. You'll see there's a little bit more code here. It's a little bit more complicated. Okay, but it's more efficient. Okay, the initialization is similar. We have this distance vector which represents the shortest path from the source to all different destinations, but the invariant is different. So in this case, we're going to be we introduce a notion of visited nodes. We have the set of nodes, and we're going to visit in each of these loops. The loops of the algorithm each time visit one node. We visit the closest unvisited node, closest from the to the source. And by doing that in that order, at every iteration of this loop, we have the shortest path to the visited node. And for all the other nodes, we have the shortest paths that only use visited nodes. So in other words, what we do with Dijkstra's algorithm is we start off saying that no vertices can be used. So remember, in Bellman-Ford algorithm, in the loops, we were saying, okay, the length of our paths is increasing. At first, we have paths of length 0, and they get longer and longer. Eventually, they're long enough to give us the true optimal for any graph. Okay, in Dijkstra's algorithm, there's a slightly different kind of growing. That growing of solutions is based on the set of vertices you can use. Okay, at first, we say you can't use any vertices except the source. Then we say, okay, you can use one vertex, then you can use 2 vertices, and then 3 vertices, and then 4 vertices. Eventually, you can use all the vertices, like travel through all the vertices to get your shortest paths. And at that point, we'll have an optimal solution. But we go through the vertices in a particular order, which is to say we always include the closest ones first. And if we do that, then that'll give us an algorithm that can effectively and efficiently finds the shortest paths to all the destinations. Okay. So in this while loop, we go through this for like n times, which is to say the number of vertices. We start off, we create a queue of all the vertices, because we're going to go through them. We're going to pull vertices off the queue to visit, to include in the list of nodes that can be visited. And we have to do that in a particular order. And for this, we're going to want to use a priority queue in terms of the distance to make it efficient. But you don't have to if you don't care too much about the efficiency. But basically, we consider in each loop one new vertex, and that is going to be the one that has so far the minimum distance to u. Okay, and at first that would be the source itself. So we start off with the source as the first vertex we're visiting. Whenever we visit a vertex, we consider all of the edges on that newly visited vertex and say and relax just on those. So we don't do a relaxation across all the edges on the whole graph, just the edges that are neighbors on that newly visited vertex, because we know that those are the only ones that might benefit from adding this node to the path. Okay, and it's the same check of relaxation to get that right. So the invariant here is that at time in every loop, if we have visited a node, in other words, if this node is one that we have pulled off of the queue, this set of vertices, then we have the shortest path to that node. And for the other ones, we have the shortest path that uses the visited nodes. Okay, the runtime complexity here is shorter. If you implement it very simply, it's order number of vertices squared. If you use a priority queue here in this step where we're getting, in the simple case, you scan through all the vertices to get the one with the shortest distance. If you use a priority queue, you can get that in like v log v time instead of, you get that in log v time instead of in v time. And then the number of edges here is because when you consider in this inner loop here, you consider a neighbor, an edge basically twice in total, because it's going to be a neighbor of 2 edges. That's how you get a total of E here. All right, so that's a little bit abstract. Let's look at that example again. Same example, but this time using Dijkstra's algorithm. So we initialize it in the same way with like distance 0 for most of these, but infinity for the others. Okay, and we iterate. Okay, so we start off, we don't really have an I that's meaningful for the loops, but we have a set. We have a set Q of unvisited nodes, which initially is all of them. So actually, instead of drawing it like as a set, because I don't have labels for these, what I'm going to do is kind of mark them as visited or not visited. So I'm going to use purple to circle. So we're going to say purple equals a visited node. Okay, so we'll always visit the closest node. And by closest, I mean the one that has the smallest number for its distance from the source, right? We're storing that in a table, and we also should put it in a priority queue to efficiently get the shortest one out. But at first, this 0 clearly is going to be the shortest, right? So we're going to visit this 0. What does it mean to visit a node? So I guess this purple is hard. It's this let's just say purple circle. If you can't see the color, just the circle means that we're visiting a node. Yeah. So what does it mean to visit a node? So that this U here is the newly visited node. We just look at the neighbors of U and do a relaxation on the edges that are to the neighbors. So we just consider these edges and do relaxations. So that gives us these relaxations to distance 1 and 3 here, right? That was after, and then we're done with that loop. So that was a quick loop. We only have to consider 2 edges in that loop. That's why this is more efficient. It strategically considers the edges only when they're necessary in the most efficient way, starting from the source outward. Now, next loop, we have to pick another node to visit. How do we visit? How do we choose? We choose the vertex in queue, meaning the ones that were not visited, the ones that are not circled, with the minimum distance. Which one of these has a minimum distance? Stop and think about that. Who are we gonna visit first? What do you think? It's this one, because it has distance 1. 1 is not a minimum. This 0 doesn't count because we already visited it. We're just considering the remaining ones. Okay, so 1 is less than 3, so we visit that one. We consider these edges and do relaxations. And by doing that, we end up getting here, instead of 3, we get 2, right? Because this 1 plus 1 is the relaxation there. Gives us 2 here. Here we get a relaxation. Instead of infinity, we now have 1 plus 3. Sorry, that 3 stays. What I meant to erase was this infinity. This infinity becomes 4. Okay. And this one here, I try that. That doesn't give us anything new. Okay. So at the end of the second round, I have these distances and I have these 2 nodes being visited. Now, let's look back at the invariant. The invariant said that the distance to every node was the shortest if that node that we're considering was visited. Otherwise, it's the shortest using visited nodes. So we have the shortest path to these 2. So 0 and 1 are in fact the shortest paths to these 2. For this one, the invariant says that we have the shortest path that only uses the visited nodes. So yeah, actually 4 is the shortest path that only uses these 2. If we are forced to only use these 2, then 4 is the shortest we can get to that. The 3 that we're eventually going to get uses a node that has not yet been visited. So it's okay that this is not yet the optimal. We don't expect this yet to be optimal because we haven't visited everyone. All right, so next iteration, who do we visit? We have to pick a node to visit. It's this one because it's the closest, right? 2 is less than 4. Visit that. We relax on these 3 edges. That gives us a better solution here, a better distance. Instead of 4, we can relax 2 plus 1 gives 3. Okay. And finally, we would visit this last one. But of course, at that stage, since this is the very last one, there's nothing that changes. Okay. At least for this one, it doesn't change. It could potentially change. Well, no. If it's the last one, I think nothing changes. Okay, so that is Dijkstra's algorithm in a nutshell with a very simple example. Glad I got through that without making big mistakes, I think. This picture here is kind of a cool animation that shows Dijkstra's algorithm in motion on a graph where the weights of the edges are actually the physical distances. If you were to measure the pixels between the points, that's what the weight of these edges are. And you can see the way it works by it is visiting the closest unvisited one. And the red lines show the shortest path tree that's built. I didn't really stress it, but in the algorithms I was showing, there's always, when you do a relaxation that works, you assign the predecessor to a node to be the place where the relaxation happened. And so you end up getting this path that is the shortest path tree that tells you if you want to get to any of these visited nodes, all the ones that are reached right now have been visited. The shortest path you take is shown in red. Okay, and the relaxations, it keeps visiting the ones that are like next closest that have not already been visited. By doing it in that order, eventually it gets the shortest path, not just to a destination, but actually to every destination in the network. That's one of the cool things about Dijkstra's algorithm. And just like the other one, there's a demo online you can do, so I encourage you to do that. Check that out. I already did the example on the whiteboard. Now, comparing those two, Bellman-Ford is simpler, but it's slower. Dijkstra's is faster, a little bit more complicated. Bellman-Ford handles negative cycles better. Dijkstra's algorithm does not handle that well, and we didn't really see why. And we're going to use both of these. In your third project, you're going to implement both of these. In a sense, although Dijkstra's algorithm you'll implement directly for the link state algorithm. If you have the full information about the whole graph, you might as well use Dijkstra's algorithm because it is more efficient. Bellman-Ford can be adapted into a distributed implementation called the distance vector algorithm, which I'm going to show next. And this is what's used by BGP. Okay, the distance vector algorithm. With the distance vector algorithm, the nodes each node operates in parallel at the same time, and it keeps information about how to reach all the destinations in the network that it knows about. And what the next hop is to reach those destinations as quickly as possible. Okay. Each node knows the cost to reach its direct neighbors, and it makes a choice about which of the neighbors it should use to reach everyone else in the network. Okay. Your distance vector, gives the distance to reach every other destination in the network, and it also indicates which next hop you'll and you give that. Sorry, your distance vector lists the distance from you to everyone else in the network. That's what this formula is showing here. And when you give that to your neighbor, what you're telling your neighbor is, okay, if you want to reach everyone in the network, here's the distance it takes to get from me to all these other destinations. And you can use that to make a routing decision, because you know that the cost for you then to reach those destinations, if you want to go through me, is the cost of the link from you to me plus the value that listed in my distance vectors. Okay, so if I know I can reach this destination in cost 3, and you can reach me in cost 1, when I tell you I can reach that person in distance 3, then you know that you can reach that person in distance 4 if you go through me, across that link of cost 1 plus the 3. Okay, so that's a simple kind of addition there you can do. If all of your neighbors give you their distance vectors, which is to say if all your neighbors tell you what the cost is for them to get to their everywhere else, if they know what the shortest paths are from there to everywhere else, you can use that to plus the distance from you to that neighbor to determine which neighbor is the best choice to reach all those destinations. Okay, so I think maybe a picture will make that more obvious, or an example will. But so distance. But the trick is though, that these distance vectors have to be built up over time, because at the beginning you have very little information. All you know is who your neighbors are and what the links are to reach those neighbors. So if we look at a picture, let's erase what we had before. Should have a piece of paper or a cloth instead of my hand, but we have a bunch of nodes. Basically, this is an algorithm that works on nodes that are all kind of working independently. They all have neighbors. They don't know about the whole network. They just know about their locality. Imagine this is the internet, a huge network, because we're going to use this for the internet with BGP. You know about your neighbors. You know what the costs are to reach those neighbors, and so at first, this one has a distance vector. This is A. which has 4 numbers. If these are all ones, then it might be cost 1 to reach all these different neighbors, which might have names like neighbor B, C, D, and E with cost 1, 1, 1, 1. So this is kind of a distance vector that this node A, when it starts up and it sees the connections it has to these neighbors, it gains the knowledge that it can reach these destinations. I guess you can also include yourself perhaps in that list just to be complete. You can reach these 5 destinations with a certain cost, like a certain distance. And you can share that with your neighbor, and then your neighbor can use that to build out more information. So this neighbor here, C, if this information, this distance vector is communicated to C, now C can actually gain information about reaching D. Like initially C might have had a similar bit of information about its neighbors. When it gets information from A about reaching B and D, it can say, oh, now actually the distance vector for C, after it gets this information from A, might include, for example, the fact that C can reach A in cost 1, C can reach B in cost 2, and can reach D in cost 2, can reach E in cost 2, and of course, just for completeness, maybe reach C in cost 0. Okay, so this is a distance vector that C might build after it gets this information from its neighbor. Supplementing this, it should also perhaps say what next hop it's going to use, like how it's going to get there. So to get to A, it's going to go through A. To get to B, it's going to go through A. To get to D, it's going to go through A. To get to E, it's also going to go through A. But to get to C, it doesn't really have to go anywhere. It just kind of goes through itself. Okay. So this is we call this a distance vector. These are both distance vectors. This one I didn't put information about what this third column of what route or what path and what next hop, let's say, you need to get there. Okay. But so distance vectors can be, this is an iterative algorithm where each node computes the cost to get to everywhere else in the network and what the next hop is to get there by choosing among the distance vectors of your neighbors. So to make these choices, you have to have you keep distance vectors from all your neighbors. If you have all your neighbors' distance vectors, you can choose among them to figure out which one is offering you the best choice, the best path to get to a destination. So for example, just to make that a little bit more clear, if C got this distance vector from A, but it also, let's say it was connected to F here. If F has an inferior connection, let's say it has a connection like this, where it is connected to E with cost 2. F might have a distance vector at some point that says, okay, I can get to E in cost 2, through myself. Yeah. And, I can get to myself in cost 0. So this might be some information that's shared up to C. When C gets this, it would store it, and when C has that new information and wants to recompute its own distance vector, when it looks down at of course, it would have to add F because it now has a cost, it has a way to get there in cost 1 through F. But when it's considering E, this node here, it needs to choose between two neighbors. It either can go 1 plus distance vector of A to get to E, so 1 plus 1 is 2, or 1 plus distance vector of F value of E, which is 2. So 1 plus 2 is 3. So it's going to choose the 1 plus 1 equals 2. It's going to choose A as the next hop to get to E instead of F. Although F is viable, it's possible, it's not the most efficient way to get to E. So the iteration of this algorithm involves nodes waiting for changes. Those changes could be local links changing. So I showed in this diagram the costs on edges. These edge costs could change. When that happens, you need to recompute. So if you're A and this node, this edge here has a cost change, then you would need to recalculate your distance vector. You have new information. Other new information is a distance vector arriving from your neighbor. Okay, so two different kinds of new information. You wait for that new information. When new information arrives, you recalculate your own distance vector based on that new information, and you send your distance vector to your neighbors. That propagates the information. They, in turn, are going to be waiting for new information, including distance vectors. So this iterative process of waiting, recalculating, and notifying will propagate changes. I mean, the actual changes are going to be links being having cost change, new links added, links being deleted, maybe new nodes joining the network that introduce links, new destinations being added through links. All that new information is going to be introduced, propagated throughout the network by distance vectors step by step. Okay. So I think that my description of the distance vector algorithm is more clear than the book's. So I suggest you try to learn distance vector just from my slides instead of from the book. And here's what I'll do. Next time at the beginning of the lecture, I will go over a more extended example of distance vector algorithm just to reinforce it, because I think this was a little bit too short. But I don't want to go too much longer on this one lecture because it's been pretty long. Okay, and this is something you'll have to implement in a third project, which at this point, if you're watching this when I release it, is probably way ahead of where you are. I haven't released that project yet, but it's coming up and you'll have to learn it. Okay, so to recap, today's lecture started off talking about routers, what's happening on inside with multiple queues. We saw buses and crossbars as two different ways to interconnect input and output queues. Weighted fair queuing is a way of prioritizing packets so that different classes of traffic get different priority. And then we talked about routing algorithms. These are what determine the forwarding tables in routers. And what we have a shortest path problem on a weighted graph. That graph represents the network. The weights represent delays, typically. We have both centralized and distributed approaches. So what I was just talking about with distance vector, that's a distributed approach. Again, I realize that I went over it pretty quickly. I'm going to repeat that next time a little bit more. But with the centralized algorithms that have full information, Dijkstra's algorithm really is the go-to, the gold standard there, at least in terms of the simple algorithms, relatively simple algorithms. It's centralized, it's fast. It's actually used by network protocols such as OSPF, Open Shortest Path First, network protocols where you have information about the whole network in one place. And that's typically when you're making decisions within your own network about your own routers. So within an AS, that means autonomous system, which we'll explain more later on in the class. To do that, actually, routers would... to share that information, you can have routers flood link information to the entire network, which we didn't really mention, but I'll come back to that later. And then once the routers get all the information, they can solve this shortest path problem in one place. The alternative to that is based on the Bellman-Ford algorithm, but it's a distributed implementation called the distance vector algorithm, which ends up being used by BGP, the Border Gateway Protocol, which we'll talk about later, which is what connects the internet as a whole. So initially, these routers, when these distributed actors in the network only know about their neighbors, the links that go directly from them to neighbors, they use that to build up information about reaching just those few destinations and share that with their neighbors. And then their neighbors share that with their neighbors, and their neighbors share information back to you. And whenever you get new information from your neighbors or from links that you observe, you update your information. Gradually, you build up more information. And I'm not going to prove it in this class, but this actually will terminate and converge to the optimal shortest path for everyone to every destination. as long as the changes stop in the network. There'll be some delay, but you will eventually reach an optimal solution. Okay. And I'll talk a little bit more about the details of broadcast and distance vector, this flooding, in the next lecture. Okay. All right. Thanks for joining me, and see you next time.